So today I'm going to be explaining another important paper with the title Simplifying Node Classification on Heterophilous Graphs with Compatible Label Propagation. This paper in 2022 in the Journal of Machine Learning Research. Graph neural networks have been predominant for graph learning tasks. However, recent studies showed that a well-known graph algorithm, label propagation, combined with a shallow neural network can achieve comparable performance to GNNs in semi-supervised node classification on graphs with high homophily. In this paper, we show that this approach falls short on graphs with low homophily, where nodes often connect to the nodes of opposite classes. To overcome this, we carefully design a combination of a Bayes predictor with LP algorithm that enjoys a closed form solution as well as convergence guarantees. Our algorithm first learns the class compatibility matrix and then aggregates label predictions using LP algorithm weighted by class compatibilities. On a wide variety of benchmarks, we show that our approach achieves a leading performance on graphs with various levels of homophily. So like previous videos, we had this notion of homophily ratio. So they define for both edge and node. So we focus on semi-supervised node classification task on a graph. We aim to infer the unknown class labels for all U. In addition, tau is split into two subsets, training and validation set, to prevent overfitting. And we have early stopping to prevent overfitting. Also, they introduce notion of compatibility matrix. Like previous video, we had compatibility matrix. But here, compatibility matrix are defined like to capture the fraction of outgoing edges from a node in class I to a node in class J. And here they define homophily ratio of an individual node. So this is our overview of compatible label propagation. First step is predictor. We have a Bayes predictor. MLP makes class predictions. Makes class predictions for each node using only node features. And the second step, we have global compatibility matrix between classes. And finally, propagate class predictions with the LP algorithm and get the classes for test nodes. But what is this simple Bayes predictor? It does not rely on graph structure to learn prior predictions. So we train a model to minimize that, where x sub v is the available feature of node and y is the true class. So we adopt a simple multi-layer perceptor. So there is no graph structure here. But the focal idea of compatibility matrix is summarizing the relative frequencies of classes between neighbors. Under the semi-supervised node classification settings, we only know the class labels of a small fraction of nodes. We derive the preliminary class labels of unknown nodes as the Bayes prediction. We treat validation set nodes as unknown nodes, which will be used to evaluate the performance of LP step and pick up the better final predictions. So the training mask M is defined like this. And then we use this M, this mask. So the preliminary knowledge of class labels can be represented like this. And this is Hadamard product here, this element-wise product. Then we estimate this compatibility matrix using this B hat. It calculates the probability that a training node of one class is connected with a node of another class. S is the Sinkhorn-Knopp function and ensures H hat is doubly stochastic. After obtaining this estimation H hat, it propagates the knowledge about node class labels with the guide of H hat over the graph. The key idea is that the edge weight of the message when we go from U to V in the label propagation algorithm depends on both predicted classes of sending and receiving nodes. That contrasts with the previous works where edge weights depends only on the sending node class probabilities. So for each edge, we define an edge weight like this, that this probability depends on probabilities that node I, so this weight F, it only, as you see, it only depends on the probabilities that node I is connected with some class K. Now let B hat and D hat be the final node prediction matrix and the base prediction respectively. Now AF is the fixed weight adjacency matrix, and so we can have the final node classification like this. So the final node classification prediction can be computed via linear matrix operations. So they did experiments on Chameleon, Squirrel, and other data sets. They compare even the MLP, graph convolution, graph attention, all of them to this model. For example, from MLP, which doesn't even care about structure of a graph, you only have 2% improvement.